So remember what I said last time, that this section is sort of an odd section in the sense that it doesn't really give any new method. It's rather just a different point of view of the method that we've done so far. Okay, and so remember the definition that we have. Like we have this thing called the fundamental matrix. Right, and this was a function, right? Right, this was some function. It was a matrix value function, right? And each column of the matrix was a member of the fundamental set of solutions, right? So you had x1 to xn, a fundamental set of solutions, right? And then you took those vector valued functions and you put them into a matrix, and you call that thing the fundamental matrix, right? And so this was fundamental set of solutions to the vector equation, right? The homogeneous vector value equation, vector value differential equation, right? And we said that we made the observation, the obvious observation that this thing satisfied its own matrix value differential equation, sort of obviously, right? So that was the fundamental matrix. And then we have this thing called the special fundamental matrix, right? The special fundamental matrix at time t0. And that was just a fundamental matrix that equaled the identity at that time, right? So it was, we call it phi t was a fundamental matrix such that phi at time t0, was the identity matrix, right? And that was the special fundamental matrix at time t0. Okay, and then we said that we made the sort of obvious observation that if you take the fundamental matrix and multiply it by any fixed vector, then you get a solution to the homogeneous equation, right? And as Blake observed, well, that's no miracle, right? Because if you take this thing and multiply it by a vector, you're just taking a linear combination of the columns, right? So you get you're going to get something that's in the span of the fundamental set of solutions, so it's still going to be a solution. Okay.
That's second. Sorry, this is kind of matrix of solutions.
Say again?
The matrix of solutions.
This is the matrix of solutions, right?
Yeah, with your coefficients found.
So if you take, what I'm saying is that you take this guy and then multiply it by some fixed vector.
Okay, yeah.
Right, multiply it by some fixed vector. Well, and we're saying that this solves H, right? And we can see that in two ways, either by differentiating it and saying that it does solve H, right? Because when you differentiate it, you get, right, for the derivative of this thing is just, this thing is constant, so the derivative will just be on this guy. You get psi prime, C1 through Cn, right? But psi prime is a psi, right? Psi prime is a psi.
So you can just solve for the constants knowing that the identity matrix is like.
Oh, yes, you can.
Yeah.
Yes, you can. Yes. So that's what we're going to say next. Okay, that's what we're going to say next. So, okay, so, yeah, so I guess we don't need to say it again. You see that this thing solves H by this, right? Because its derivative equals A times itself, right? So this thing solves H, right? And or you could have seen it the other way by recognizing this as a linear combination of columns, each of which solve H. Okay, and so so let's make another simple observation. for the system, and we impose an initial value condition. The initial value condition being that we add an initial value condition to H. Okay, saying that at time t naught, we want to get the value x naught out of it. Okay. It's easy to do. It's easy to find a solution. Here it is. Wait, let me see it this way. Let me see if I can make you tell me what it will be. So here's this thing x naught, right? And we know that if I take psi times it, then that's a solution, right? That's a solution. But that's not the right solution, because I want the solution to, at time t naught, to be x naught, right? And at time t naught, this is not x naught, it's psi t naught x naught, right? It's the wrong one, right? So how can I sort of toggle this? How can I, sort of toggle this so that I do get, so maybe I don't want to multiply it by x naught, right? But I want to multiply by some other vector, so that at time t naught, I get x naught. What vector should I multiply by to get x naught at time t naught? So I mean, you want to, let me say it this way. So yes. So think like this. We can create all sorts of solutions, right? Like we can put in anything here, right? We can put in anything here, C, okay, right? And we want C so that psi t naught times C is equal to x naught, right? Well, what should C be? What should C be? Here it is. You've got a matrix times C, you've got an invertible matrix times C. Must be equal to x naught, so what should C be? Just x naught times the inverse, right? X naught multiplied by on the left side by the inverse matrix. Right? Okay, so just take C to be psi t naught inverse x naught. Right. That's the solution. Right. Because, right, it's a solution, right? It's a solution, and at time t naught, it gives us x naught.
And they give you the identity.
So it doesn't give you the identity. Well, at time t naught, right, this thing on the left will be the identity.
Mm-hmm.
Yeah, that's true. Right, so what does that say? That you've actually created a special fundamental matrix. Right, so notice, right, that this thing here is the special fundamental matrix at time t naught. Right. So we can not only solve initial value problems, but we also have a way of creating this. If we have a fundamental matrix, we can get a special fundamental matrix for whatever time we like.
I have a question with accepting that. Is there a difference between A as a function of T, and what's the difference between a T and A as a matrix? I'm just wondering if there's a difference. Because you write like A as a function of T.
Yeah, I think it should. I think whenever I write A in this case, in this section, whenever I write A, I mean A of T actually. So A is a function. A is a function. But I guess in all the examples, it's constant. So, no, you're right. I'm sorry, these A's should not be functions of T's. They should just be A's. Sorry.
What is A, the matrix of coefficient?
Yeah, it's just a matrix of numbers, like in the problems we did before. Okay. Is everyone okay? Right. We've got the fundamental matrix. We say, look, we can use it to solve. If we want to, we can use it to solve initial value. If we impose an initial value condition, we can find solutions for it. Blah blah blah. If you want, maybe do it. I'll do an example, but this example will reveal that in some sense we don't need to do this sort of stuff. Okay, so an example of using the fundamental matrix to solve an initial value problem. So anyway, let's do it. So you have, say, a system. X prime is 1, 1, 4, 1, 4, 1, x. Okay. And then you can get a fundamental matrix. Either 3t, 2 e to 3t, e to the minus t, minus 2 e to the minus t. Okay. And the thing is that to do that, we have to run through our previous technique, right? We use find the eigenvalues. Like the eigenvalues are going to be 3 and minus 1, right? And then find the eigenvectors, 1, 2, and 1, minus 2, right? So we in the meantime, between here and there, we need to do all the work that we did before. So we're not really saving anything. Okay, right? So we get one solution, namely 1, 1, 2, e to the 3t, and another solution, 1, minus 2, e to the minus 2. Right? We get fundamental set of solutions and we put them into the matrix. Okay. Then, right, so here is our homogeneous problem, and somebody imposes a condition and says that x at time 0 needs to be whatever, 1, 5. Right. It says I want a solution that has values 1, 5 here at time 0. Right? And how would you do it? If somebody asked that, how would you do it? Yeah, you would just take the 1, 5 and solve, right? You would say, well, look, right? I know that if you didn't want to use matrices at all, you would say, well, look, I know that the solution, all solutions look like C1, 1, 2, e to the 3t plus C2, 1, negative 2, e to the minus 2. Right? That's the general form of the solution, right? And so I want C1 and C2 such that this at time 0, right? This at time 0, this at time 0 equals 1, 5. Right? In other words, 1, 2, 1, minus 2, C1, C2 equals 1, 5. Right? And then you would either use Gaussian reduction, or you would say, well, look, this is actually an invertible matrix, and so I'm going to just multiply by the inverse on both sides. So that is one way of looking at it, and the other way of looking at it is to say, well, I know that that my solution is going to be the matrix, right, the fundamental matrix, 2b 3t minus 2 minus 2, times the inverse of the matrix at time 0, right? That's 1, 1, 2, negative 2, inverse, right? Times x0, 1, 5. And you see that it's exactly the same thing. Right? We're getting, what combination are we getting of these columns? We're getting C1 and C2, right? C1 and C2 from here. Right? C1 and C2 is 1, 1, 2, negative 2, inverse 1, 5. Right? And so you see both ways are completely identical. It's just a different point of view. Okay.
Wait, did you do it? I'm a little confused. So did you do it one way and then you did it another way?
Yes, yes.
What is the other way? Doesn't that involve doing it this way? Or-
In some sense, yes. So, I mean, you could say I've done it one way, I've done it the other way, but you could say I did it facing one direction and then I did the same thing while I was looking in the other direction. You know, it's almost completely identical.
So would you have to like, do that out in order to get the answer?
Yes, yes, yes. In either case, you see, no work is saved whichever way you go, right? If you do it by thinking about the general form, the form of the general solution, and then using, you know, Gaussian reduction or whatever, you'll get C1 and C2 done, right? And you figure out that will give you the solution to the initial value problem, or you do it this way, but you see that you're ultimately going to have to invert the matrix. You know, you're going to have to do the inversions,
Which means you can use Gaussian elimination here.
right? Or you use the adjunct thing for this. This is pretty simple.
Just quick question. So phi is x, like that's the solution to 2x. Like in our original homogeneous equation.
This is the matrix with fundamental solutions. Each column is a fundamental solution. So to get it, we find the fundamental set of solutions and then just put them in the matrix one. Okay. Okay. And okay. And you know, notice that if you wanted to, you know, you could find. Okay, so you know, we can get this special fundamental matrix by doing this. I'm not going to do the example. So okay, so let me. Let me go to a topic that will seem sort of unrelated, but actually it is very closely related. So this is called the exponential matrices. And you're taking the exponential, you're taking the x of the matrix. So definition. We are going to, you remember what we said last time, right? That if you're thinking about scalars, right, and somebody asks you, you know, I want a function that satisfies something like this, well then it's the exponential function. And can we do something like this for matrices? And the answer is yes. So given a matrix A, we define x of A, or e to the A, if you like, as by using the power series. Right? We'll use the power series and put the matrix into the power series. Right, so this is I plus A plus 1 over 2 factorial, A squared plus 1 over 3 factorial, A cubed, et cetera, and you hope that that this actually converges to something. So we're sort of this does converge, but we're not going to talk about it. So all of the entries are going to converge. So it is possible to show that this this definition makes sense, right? Because you don't, maybe you're worried that this thing is infinite, right? You've got an infinite sum here, right? Just like if you, back in the, UBS, SVN or factorial, and maybe you're worried that thing, just diverges. But this thing, as you remember, using the ratio test or something, this thing converges everywhere on the real line, and this thing will also converge for all matrices. But we're not good. Okay. Okay, and so that sort of, so we can consider the function x of at, right? This is the analog of e to the 18, like the solution to that scalar value equation that we had just a second ago. Right, this is where, so t is your variable, right? The scalar variable. So x of 18, that is the identity matrix, right? Plus summation a to the n, t to the n over n factorial, and n equals 1 to infinity. Okay, and if we differentiate both sides, say, we get the derivative of this thing on the right hand side. And so what do you see happens? Do you see what's going to happen? Well, the derivative of I is 0, right? And then when we differentiate this sum, what happens? So, turns out that you can differentiate termwise. So that's sort of a cheat, right? Again, the reason that you can do that actually has to do with the convergence of the function. Okay, so can pass differentiation through the infinite sum because of something called uniform convergence, which unfortunately is not covered in the prerequisites for this course. It's covered in 131 or sometimes in 132. So in any case, this function does converge uniformly, and so you can pass it through. And then you just differentiate, right? And you see what happens. Right? You get, well, summation n from 1 to infinity, n, a to the n, t to the n minus 1 over n factorial. Right? And it's just like the old it's just like the old exponential function. Brian, you have a question?
No, sorry.
So it happens just like with the scalar value exponential function. Well, you see what happens when you get the n crosses up here. Down here we get n minus 1 factorial, right? Right. And if we pull an a out of it, we get n from 1 to infinity, a to the n minus 1, t to the n minus 1 over n minus 1 factorial. Right? But you recognize that, right? That is just, if we shifted it to start at 0, this would be n from 0 to infinity, a to the n, t to the n over n factorial, which is just e to the 18 again. Right? So we get a times e to the 18. And so this function does satisfy the differentiation that your old friend also satisfied. Yeah.
Is this related to the Banach contraction mapping principle? Because in my 131 class, we talked about that yesterday. So is this like an iteration type thing?
This, I mean, it's not so fancy a thing actually. No, I don't think it's going.
Okay.
Yeah. No, it's this. I don't think so. Yeah. Almost definitely not.
Okay.
Okay. So what do we see about this thing? Well, we see that if we let that this function plus this function satisfies one, that its derivative, let's call this function e. The derivative is a e, right? And two, right? Two. So this is a matrix value function. This matrix value function satisfies this, and also e times 0 is a. Right? E times 0 is a, and so what you see is that this. What is this? Right? In our previous language, this thing is et, right? X at is the special fundamental matrix for x prime equals ax, right? At t equals 0. So this would be a way, if somebody gave you a matrix and said, what's the solution to this homogeneous equation? You could say, well, I can take the exponential function of it, right? And then I'll get the special fundamental matrix, and that will give me, that would give me actually the fundamental set of solutions. But as you see, it would be awful to do it, right? Because in order to find the x of at, well, you need to take an infinite sum, and you need to take infinite powers of this thing, right? So it's not, theoretically it's simple, but practically it's not so practical.
Can you do this using numerics?
So the way one actually does this, can anyone think of a case where taking x of a matrix would be quite simple? Like what matrices would be simple to take powers of an exponential?
Natural log, or the tracing natural logs.
It's still troublesome, right? Because you've got to take powers, right? So you're taking a square, a cube, and blah, blah, blah.
What, 12 zeros?
If they're all zeros, okay. Sure. Maybe something a little bit. What if you have Gabriel?
Either diagonal or triangular.
Diagonal, triangular. I think is still not going to be so simple, but certainly diagonal. Right? If you have some values, lambda 1, lambda 2, lambda n here, right? And you take powers of this, right? The powers are just going. When you take powers, it just amounts to taking powers of these guys, right? And so I think it's a homework problem for you to show more clearly, but it's sort of obvious that the x of a t, this is just going to be the matrix e to the lambda 1t, e to the lambda 2t, e to the lambda nt. Right, Blake?
Two guesses. First is if it's just only values in the first row and then zeros everywhere else.
Okay. And second guess?
Just that identity matrix.
Identity matrix, so that the identity matrix will fall into this
Yeah.
class, right? diagonal matrices.
What if it's idempotent?
If it's idempotent, well, then you've got the same matrix, right? Basically, from the second, you got the same matrix all the way through. So yeah, that would also be easy. But the one that we're going to be really focusing on is the diagonal matrices, and to make it a little bit more interesting, we'll say also the diagonalizable matrices, right? If you have a diagonalizable matrix, right? In that case, your matrix A is equal to some conjugate of a diagonal matrix, right? And in that case, taking powers of it maybe is not so bad, right? Because you know that, right? In that case, so if A is diagonalizable, like this thing happens. Well, in that case, T inverse is a diagonal matrix, right? And if you look at the square of the diagonal matrix, you see you get T inverse, T inverse. That is T A squared, T inverse. Right? So A squared then is easy, right? A squared is just T inverse diagonal squared T. Right? And the same for all n. Right? A to the n is actually easily calculated if your matrix is diagonalizable.
What do you mean by, I'm just getting a little confused, like, what do you mean by calculated? Like, AN is calculated?
You can, if somebody asks you to calculate it, right? Somebody gives you a matrix and says, what is this matrix to the n power? Well, how do you do it? Well, you have to start multiplying, right? But if your matrix were and I said, what is A to the thousandth power? You're like, what? There's not much you can do. You just start multiplying, right? But if your matrix is diagonalizable, well then you say, well, all I need to do is take the diagonal matrix and raise it to the thousandth power, right? That would just be the entries to the thousandth power of the diagonal matrix, right? And then I conjugate the end.
And what is T represent?
T is the transition matrix that diagonalizes your matrix.
Should we, yeah, we did that in section 7.3.
We will talk about it now,
Okay.
but you may remember it from when you're out.
Yeah, and one more thing, when you were saying like EXP with like the diagonal matrix T, and you were saying like that the Homer problem or whatever is to show that that's equal to the diagonal matrix with E to the that power of
Yes.
So is that just a manipulation of exponents and matrices, or?
I'll let you think about it. Then it'll be a Homer problem. Okay. Okay, do people want to see a review of diagonalization? Do people want to see a review of diagonalization? Yes? No? Okay. Let me sort of quickly review diagonalization. Okay. So I mean, here is very roughly what you want to remember, that if C1 to Cn are a basis of eigenvectors, with eigenvalues lambda 1 to lambda n, so given the matrix A, if you have a matrix A and you have a basis of eigenvectors, then it turns out that if we let T be the matrix of eigenvectors, then T inverse AT is a diagonal matrix. A diagonal matrix with the eigenvalues down the diagonal. So anybody, whenever you have a basis of eigenvectors, well, you can use that basis of eigenvectors and conjugate your matrix, and you get a diagonal matrix. This is actually sort of an obvious statement.